Design and optimization of microstrip antennas with defected grounds structures using HFS. My project will focus on improving microstrip patch antennas by integrating defected ground structures, which is short for DGS. These structures will modify the current distribution to enhance performance in terms of bandwidth, return loss, and radiation efficiency. Simulations are carried out in ANSYS, HFFS, using several DGS geometries, including H-slot, U-slot, and ring shapes on antennas tuned to operate at 5.8 gigahertz. Traditional microstrip antennas, while they are compact and easy to manufacture, they're limited in bandwidth and radiation efficiency, which can hinder their performance in demanding applications. And now incorporating defective ground structures, as I mentioned before, DGS, it offers a low cost and space efficient solution to overcome these limitations by improving key electromagnetic characteristics. By using HFFS simulation, we will be able to evaluate and optimize antenna designs without the immediate need for physical prototyping, which will save us time and resources. This project is feasible from the technical, economic, and academic perspectives. HFS is available at Inaue and allows for accurate full wave simulations. Since this phase is entirely simulated based, there are no materials costs involved. Theoretical support from well-established literature and access to institutional equipment make it ideal for student research. Well, the main objective is to simulate and analyze the performance of microstrip antennas with different DHS patterns specific goals. The antenna uses an FR4 substrate that equals 4.4 and 1.6 millimeters thickness. The patch dimensions are 38 times 29 millimeters and will be designed to operate at 5.8 gigahertz, as I mentioned before. The ground plate is 70 times 70 millimeters with variations introduced by different DHS geometries. The simulations were performed using HFS in the 4.5 to 6.5 gigahertz range. The GGS types that were used were H-slot, U-slot, ring, and periodic lattice. The regulations that were applied are the following: IEEE STD 149 to 1979, EEE STD 145 to 2013, the I2RSM 1138 bandwidth, the ISO IEC guidelines, and the institutional research of academic integrity protocols. The proposed methodology. The project began with a literature overview, followed by the modeling of baseline antenna in HFFS. Each DGS variation was introduced and simulated under consistent conditions. Parametric sweeps were used to optimize dimensions and mesh refinement in ensure accuracy. The following results were documented, analyzed to compare performance across configurations, showing the feasibility analysis, the patch, the electric, and the ground. The baseline microstrip patch antenna was designed and tuned to resonate at 5.8 gigahertz, and once it was validated, 4 DHS patterns were implemented into the ground plane. Each model was optimized and simulated using HFFS. DGS geometries like H-slot, U-slot, ring, periodic lattice. Simulations shows that each DGS type improved return loss, bandwidth, and radiation efficiency in different ways. The results achieved were that all DGS enhanced designs outperformed the baseline antenna. Bandwidth increased by up to 70 megahertz, and return loss improved across all configurations. The ring DHS showed the best impedance matching, while the H slot provided the widest bandwidth efficiency were also observed. Here's the table showing the different designs, the bandwidth, the return loss, and the efficiency. The no DGS, H slot, ring, U slot, and periodic. Well, this project was successfully demonstrated that DHS can enhance the electromagnetic performance of microstrip antennas. and it will do it without increasing their size. All the design's objectives were met, and the results were validated at the initial hypothesis that I established. The key insights were that the DHS is effective for miniaturized high-performance antenna design. HFSS is actually a very powerful tool for electromagnetic simulation and optimization. Small geometric changes in the ground plane yield measurable performance gains. The project lays the groundwork for future prototyping and experimental validation. Thank you.